Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we start a new segment of our course. Up until now, we've been discussing whole numbers, and today we're going to begin a new concept called rational numbers, which may sound like a big word, but the word rational comes from ratio, which in turn comes from rate, and you may recall that in our last module we talked about the fact that you have a rate whenever you have two nouns separated by the word per, and that rates are division problems. Now, what's interesting is that if we pursue our theme of adjectives versus nouns, remember whole numbers were adjectives modifying nouns. We're going to show that fractions may also be viewed as adjectives modifying nouns, and in fact, if we choose our nouns properly, the fractions can be replaced by whole numbers. It reminds me of the story of the man who went into a pizza parlor, ordered a pizza. The counterman said, "Should I cut the pizza into 4 slices or into 8?" And the fellow says, "Well, I think you better cut them into 4 because I don't think I could eat 8. You see, the important thing is that a slice of pizza is a whole slice, but it's still what? Only a fractional part of the pizza. And how big a fractional part it is depends on how many slices you make. At any rate, with this as a brief introduction, let's go now to the board and begin our actual discussion. In a sense, we're going to show today that fractional parts may be viewed as whole numbers. And what I'd like to do to get you into the mood for this is to go through a couple of examples with you. Problem number 1 says, if 4 quarts equal 8 pints, how many pints are there per quart? Now remember, per quart means divided by quarts. See, per means divided by. See, we want to know how many pints are there per quart. So what we do is we imagine a division symbol replacing the word per. Now we have to put the proper adjectives in front of the nouns here. We were told that 8 pints equal 4 quarts. See, it makes no difference whether we write the quarts first or the pints first. You see, the adjective 4 modifies quarts wherever quarts appears, whereas 8 is the adjective that modifies pints no matter where pints appears. So since pints is over here, the 8 goes here, the 4 goes here. Now how do we do this problem? We say 8 divided by 4. See, in a per problem, you divide the adjectives, and the nouns just become what? Pints per quart. So now since 8 divided by 4 is 2, we see that we have 2 pints per quart. And that certainly makes sense. If we had 2 pints in 1 quart, 4 quarts would be 2 pints 4 times, or 8 pints, which checks with our answer. Now, let's look at a problem which is the same philosophy, but it's going to force us to invent a new kind of number. We start the same way. If 4 quarts equals 1 gallon, how many gallons are there per quart? Now notice the reading comprehension here. You hear the phrase gallons per quart. And as soon as you hear that, that tells you what? Gallons divided by quarts. Now we go look for our adjectives again. What adjective is modifying gallons? If we look back at the problem, since we have 4 quarts per 1 gallon, the 1 goes with the gallons, and the 4 goes with the quarts. Now you see, we do the same thing as we did before. We're going to have 1 divided by 4, and the label is going to be gallons per quart. And now you see we come to something brand new. 1 divided by 4. What number, when multiplied by 4, gives you 1? Since 4 times 0 is 0, 0 is too small. And since 4 times 1 is 4, 1 is too big. So the number we're looking for has to be between 0 and 1. You see, it's a fractional part of a gallon, just like a slice of pizza is a fractional part of the pizza. And what we do is we invent a new notation. We write the 1, a horizontal bar, then the 4, and we read this as 1/4, and the answer would be what? 1/4 gallons per quart. Now you see, all this has done has led to a new type of number. If this looks frightening, 1/4 of a gallon per quart, that is simply a different language for saying 4 quarts per 1 gallon. And the interesting thing is, in certain cases, you are already used to using 1/4 without becoming frightened of it. For example, if I were to say to you a half a dozen, a quarter of a dozen, somehow you're used to dealing with something like that. In fact, let's take a look at that. See, just as you would say 2 dozen, you could also write what? 1/4 dozen. But when we write 1/4 dozen, that doesn't sound too grammatical. So we sometimes read 1/4 dozen as if it said 1/4 of a dozen. And you see, basically, 1/4 of a dozen is how many? See, you take the dozen and divide it into 4 equal parts. See, it's 1/4 of a dozen. But how many are there in a dozen? 12 units. Now, if you take 12 units and divide that by 4, you're going to get 3 units. In other words, if you were to multiply 3 units by 4, you get 12 units, which is called a dozen. Do you see the idea here? And notice the division problem over here. Suppose you started with 1 dozen. 1 dozen is 12. And if you divide 12 by 4, you see you get 3. See, 1/4 of a dozen is the same as what? 1 dozen divided by 4. And if you leave the noun out, it just says what? 1 divided by 4. But you see, in this particular case, 1 divided by 4 is still what? A whole number of units. And this goes on with many things that we do. For example, how often do we say a quarter of an hour? See, the word quarter and quart have the same origin. It really means 1/4. See, 1/4 of an hour has 60 minutes. So if you take 1/4 of 60 minutes, 60 divided by 4 is 15. So 1/4 of an hour, which looks like a fraction problem, is the same as 15 minutes, which looks like a whole number problem. And let's practice some more with this. See, 1/6 of an hour, you take the 60 minutes and divide that by 6. That's 10 minutes. You see, both 1/4 of an hour and 1/6 of an hour are fractional parts of an hour. But notice that they are different fractional parts. See, 15 minutes 4 times gives you 60 minutes. 10 minutes 6 times gives you 60 minutes. Let's go on a little bit further. What's 1/5 of an hour? Since an hour is still 60 minutes, 60 divided by 5 is 12. So 1/5 of an hour would be 12 whole minutes. And by the way, you can still keep going this way. See, 2/5 of an hour would mean what? You take 1/5 of an hour 2 times. You see, we just saw that 1/5 of an hour was 12 minutes, so twice 12 minutes would be 24 minutes. And again, notice what happens over here. You see, 2 hours divided by 5. You see, if the noun was left out here, you would have 2 divided by 5. Let's see what this becomes. 2 hours divided by 5. Each hour is 60 minutes. So 2 hours is 60 minutes twice, which is 120 minutes. Divide 120 by 5, you get 24. In other words, 2 hours divided by 5 gives you the same answer, namely 24 minutes, as you got if you took 2/5 of 1 hour. In other words, whichever way you feel more comfortable with, you could either start with the 60 minutes and first divide by 5 and then multiply by 2. Or you could take the 60 minutes, multiply by 2, and then divide by 5. And you see, if I use the right language now, you're going to see how this becomes easy to read. You see, in the expression 2/5, which is 2 over 5, 2 is called the numerator. The top number is called the numerator. The bottom number is called the denominator. But numerator does not mean top, and denominator does not mean bottom. When we use a big word to take the place of a simpler word, there's usually a good reason for it. After all, if numerator meant the same thing as top, and you already know what top means, why introduce the word numerator? Numerator and top do not mean the same thing. Christian Dior, or whoever it was who invented these things, never invented a numeratorless bathing suit. Numerator and top do not mean the same thing. But listen to the word numerator. It suggests the word enumerate. Enumerate means to count. To count answers the question of how many, and how many is an adjective. You see, the numerator is the adjective. And do you notice that? The numerator is a whole number. The numerator is a whole number. The word denominator suggests the word denomination. Denomination means size, and size is a noun. You see, when we break the fraction, this is called a common fraction, when we break that up into its parts, the top number is the adjective, the bottom number is the noun. In other words, we read this as if it were 2 fifths. And you see the denominator now becomes the denomination, and the numerator now counts how many of that denomination that you have. In fact, if I try to do this as a grammar problem, it gets even more complicated, because now you see, even though 2 is an adjective modifying fifths, 2 fifths itself becomes an adjective modifying another amount. For example, what do you mean by 2 fifths of a number? Let's take a look over here, again in terms of tally marks. See, I've written down 5 tally marks. To take 2 out of every 5 means, okay, I'll take 2 out of these 5, 2 out of these 5, and 2 out of these 5. What have I done altogether? You see, I have 5 tally marks, 5 more tally marks, 5 more tally marks, and each time I'm taking 2 tally marks, notice that when I take 2 fifths of a number, if the number is a multiple of 5, notice that the number of tally marks is what? 5, 10, 15. See the multiples of 5. How many am I taking from each group? 2. So the amounts that I'm taking are what? The multiples of 2. 2, 4, 6, etc. And the way we read that to make this more intuitive, and I'll show you what I mean by more intuitive in a second, I say that 2 fifths is the same as 4 tenths is the same as 6 fifteenths. In other words, at a rate of 2 out of every 5, you'd be taking 4 out of every 10 or 6 out of every 15. And notice when I say at a rate of 2 out of every 5, do you hear fractions there or whole numbers? See, at a rate of 2 out of every 5, I would be taking 4 out of 10. That's the same as saying 2 fifths of 10 is 4. You see, 10 divided by 5 is 2. 2 times 2 is 4. You see, when the 2 fifths is modifying 10, we have a fraction. But now when I'm talking about units, we have a whole number. So notice what happens over here. The numerators go up as the multiples of 2. The denominators become the multiples of 5. Notice, for example, that 35 is what? It's the 7th multiple of 5. Now, if we're counting this way, this says what? This must be the 7th fraction in the list. But since the numerators are multiples of 2, you see, the 7th one will be what? The 7th multiple of 2. In other words, counting by 2s, we come to 14 as our 7th numerator. And if we count by 5s, we come to 35 as our 7th numerator. And what that says is that a rate of 2 out of every 5, out of 35, you would be taking 14. Let's see what that says. See, what is 2 fifths of 35? 35 divided by 5. See, 35 divided by 5 is 7. 7 times 2 is 14. That's another way of looking at the problem that we just did. And if you want to see it from still another point of view, see, when you divide 35 by 5, how many 5s are there in 35? 7. So you get 7 bundles of 5. How many are you taking from each bundle of 5? 2. So you're taking 2 7 times, and that's a total of 14. Now, obviously, I don't want you to do the problem this way every time, but I do want you to see that even though I'm writing common fractions, we're thinking whole numbers. You see, we're taking one step forward at a time, and my claim is that by the time I'm through with this discussion, if you can handle whole numbers, you're going to be able to start to handle common fractions, not just comfortably, but believing that it's still a form of whole numbers. Now, just to practice, let's see if you can do a problem for me a little bit faster. How much is 2 fifths of 40? In other words, at a rate of 2 out of 5, how many would I take out of 40? And again, the mechanical way of doing this is we divide 40 by 5, which gives us 8. See, we divide by 5, then we multiply by 2. 40 divided by 5 is 8. 8 times 2 is 16. Notice I've just summarized this over here. 40 divided by 5 is 8. 8 times 2 is 16. So at a rate of 2 out of every 5, you're taking 16 out of every 40. And you begin to see how this is done. You see, by the way, we don't write this way. It takes a long time. Let me show you the fast way of doing this. See, what we do is we say, oh, 5 goes into 40 8 times. In fact, some of you may remember doing this in school. 5 goes into 40 8 times. 8 times 2 is 16. Does that sound familiar at all? See, what you were really saying when you said 5 goes into 40 8 times, you were really saying that 40 was the 8th multiple of 5. And so if I've moved out 8 fractions, if the denominator is the 8th multiple of 5, the numerator is going to be the 8th multiple of 2. You see, if I'm counting by 5s, 40 will be the 8th denominator I come to. If I'm counting by 2s, 16 will be the 8th numerator I come to. And that's how this is done. And just to show you, by the way, that you really don't change the ratios, the rates this way, let me ask you this question. Is 2/5 of 60 the same amount as 6/15 of 60? You see, these two rates look different. But the interesting thing is, I'm going to try to show you that they really are the same rate. Let's try to figure out what 2/5 of 60 is. Remember what our rule is mechanically. 60 divided by 5 is 12. 12 times 2 is 24. See, the denominator tells you the size of each part, and the numerator counts how many of those parts you're taking. Let's look at 6/15 of 40. I'm sorry, that's just a misprint. That should be 6/15 of 60. I didn't mean to do that. And by the way, as long as I made this error, let me at least capitalize on it. You see, when you want to compare numbers, you have to make sure that the numbers are modifying the same noun. For example, 3 is more than 2, but 3 nickels has less purchasing power than 2 dimes. You see, the 3 was modifying nickels, the 2 was modifying dimes. It makes a difference. So to compare 2/5 with 6/15, I want to compare them on the same amount. And so I've picked a common multiple, you see, of 5 and 15. Both of these go into 60. See, 60 divided by 15 is 4. 4 times 6 is 24. You see, if I divide 60 into 15 equal parts, each part has 4. And if I now take 6 of those parts, 6 times 4 is 24. And the mechanical way of seeing this is 5 goes into 15 3 times. 2 times 3 is 6. That's how you would have got that 2/5 was equivalent to 6/15 if I hadn't shown you that first. See, as long as I multiply numerator and denominator by the same number, I do not change the ratio named by the fraction. Of course, you may wonder, what if I was given the 6/15 first? How would you do that? That's just the inverse problem. In other words, starting with 6/15, I would notice that 6 is 2 times 3. I would also notice that 15 is 5 times 3. Since I've multiplied numerator and denominator by the same amount, the answer to the problem should be what I would have if those were missing. So in other words, not only can I multiply numerator and denominator by the same amount, I can also divide by the same amount. And that's important enough to stress. Let me just stress that for you. See, multiplying or dividing numerator and denominator of a common fraction by the same non-zero number doesn't change the ratio. And to see this more intuitively, a fraction is a division problem, a per problem, a rate problem. Suppose 2 people share a $10 gift equally. Then how would you find out how much each person paid? See, $10 divided by 2 people, 10 divided by 2 is 5, okay? And dollars divided by people would be dollars per person. Now suppose I had 3 times as many dollars, but also 3 times as many people. You see, if I triple the number of dollars, that becomes $30. If I triple the number of people, that becomes 6 people. $30 divided by 6 people, the rate is still going to be dollars per person. 30 divided by 6 is 5. So whether it's 2 people sharing a $10 gift or 6 people sharing a $30 gift, the rate, namely dollars per person, is 5 in both cases. Do you see that part intuitively? But for heaven's sakes, don't say, well, if I do the same thing to the numerator and I do the same thing to the denominator, obviously I'm going to get the same answer. No, it has to be multiplication or division. And to show you this more dramatically, let's do the next problem. Is 2 over 3 the same rate as 3 over 4? In other words, is 2/3 the same rate as 3/4? And before I do that problem, I want to show you how 3/4 and 2/3 are related. After all, if I added 1 to both the numerator and the denominator of 2/3, wouldn't I get 3/4? And you see, what I want to show you in this problem is that 2/3 is not the same rate as 3/4. By the way, the easiest way to do this is, since you want to compare thirds with fourths, a common multiple of 3 and 4. You want a number So you're going to be dividing by 3. You're also going to be dividing by 4. So you want a number that both 3 and 4 go into. Since 12 is a multiple of both 3 and 4, 12 is a nice number to work with here. You see, if I take 2/3 of 12, 12 divided by 3 is 4. 4 times 2 is 8. If I take 3/4 of 12, 12 divided by 4 is 3. 3 times 3 is 9. Since 2/3 of 12 is not the same as 3/4 of 12, 2/3 and 3/4 are not the same rate. But yet you do get 3/4 by adding 1 to the numerator and denominator of 2/3. So just because you added the same amount to numerator and denominator, don't think you haven't changed the rate. You have changed the rate, okay? And by the way, we don't have to keep dealing with 2/5. Suppose I said, how much is 3/8 of 16? Let's try something like that, 3/8 of 16. See, 16 divided by 8 is 2. 2 times 3 is 6. The answer is 6. Let's see if we can visualize why that's the answer. See, I'm taking 3 out of every 8. When I say that 16 divided by 8 is 2, it means that in 16 there are 2 bundles of 8. See the 2 8s over here? How many am I taking from each bundle of 8? 3. So I'm taking 3 from this bundle, 3 from this bundle. How many have I taken altogether? I've taken the second multiple of 3, which is 6, out of how many? The second multiple of 8, which is 16. See, at a rate of 3 out of 8, I'll be taking 6 out of every 16. Now, let me give you a hypothetical situation. Let's suppose I'm going into business, and I'm looking for a backer. I want somebody to help me. So I meet a fellow, and he says to me, I'll tell you what I'm going to do. I can't underwrite your whole expenses, but for every $5 you spend, I will reimburse you $2. In other words, what's he saying to me? I will give you back 2 out of every $5 that you spend. That means he's reimbursing me 2/5 of my expenses. Now another man comes around. He says to me, hey Herb, don't listen to him. I'm going to give you a better deal. I'm going to give you $3 back. That's more than he's giving you back. He's only giving you back 2. I'm going to give you 3 back, but it's going to be 3 out of every 8. See, what's he telling me? He says, don't worry about what you're spending. I'll give you back 3 out of every 8. And how do we read that as a fraction? 3/8. 3/8. 3 of the 8. Now the question is this. Which is the greater rate? 2/5 or 3/8? Who's giving me the better deal? And to emphasize this, let me write this in the adjective noun format. You see, 2/5 would look like this. 3/8 would look like this. 3 apparently is more than 2, but under what conditions is that true? Only when the 3 and the 2 are modifying the same noun. They're not modifying the same noun here, are they? See, it's much the same way as saying 2 dimes and 3 nickels. The 2 is less than the 3, but the 2 dimes has more purchasing power than the 3 nickels. You see, to compare which is the better deal, what we have to do is rewrite this so that the adjectives are modifying the same noun. Now, see, fifths tell us to multiply by 5. Eighths tell us to divide by 8. I'm sorry. Fifths tell us to divide by 5. Eighths tell us to divide by 8. What is a quick number that can be divided both by 5 and 8? What number is both a multiple of 5 and 8? The easiest way to do this problem is multiply the 2 numbers together. 5 times 8, which is 40, is a common multiple of 5 and 8. In fact, what is 40? It's the 5th multiple of 8 and also the 8th multiple of 5. In terms of Module 3, if you're counting by 8s, 40 is the 5th number you'll come to. If you're counting by 5s, 40 is the 8th number that you come to. Now that we have a common denomination, we're in business. Watch how we do this. We say, okay, let's compare 2/5 with 3/8. What's the best way to do this? 5 goes into 40 8 times. 8 times 2 is 16. See, 16/40, which when written out would look like this. What's 3/8? 8 goes into 45 times. 5 times 3 is 15. And what this says is, at a rate of 2 out of every 5, you're going to get $16 out of every 40. At the rate of 3 out of every 8, you're going to get $15 out of every 40. So now who's giving you the better deal? Basically what this guy is saying is, for every $40 you spend, I'm going to give you back 16. The other fellow is saying, look, for every $40 you spend, I'm going to give you back 15. So evidently, 2/5 is a better deal than 3/8, By how much? See, well, the difference between 15 and 16 is 1. 1 what? 1/40th. You see, when we compare 40ths, 16/40ths is 1 more 40th than 15/40ths. You see how the whole numbers appear here? The denominator now becomes the denomination. Now, when I write this in the language of fractions, it may appear scarier. See, we say what? 2/5 exceeds 3/8 by 1/40th. In other words, at a rate of $2 out of 5 versus a rate of $3 out of 8, you're going to be better off by what? $1 out of every 40. Do you get the idea? I need a common denomination to compare. See, for example, is 12 bigger than 1? Well, be careful. 12 inches equals 1 foot. In that case, 12 would equal 1. See, we need both the noun and the adjective to see the size. Now let's take our business problem a little bit further. Suppose now, instead of taking my two potential backers and pitting them against one another, I decide to use both of them. I say, okay, I'll make a deal with both of you. You give me $2 out of every $5 that I spend. You give me $3 out of every 8 that I spend, and then I'll give you both back a portion of the business. Now the question is, how much have they given me combined? See, that's what this next question says. How much is 2/5 plus 3/8? And you see, 2/5 and 3/8 have to modify the same noun here. 2/5 of the business, 2/5 of my expenses plus 3/8 of my expenses is how much? Now you see, what we did in problem number 7 is we showed that another name for 2/5 was 16/40. And another name for 3/8 was 15/40. Now what did we learn about addition of whole numbers? We learned that 16 plus 15 is 31, provided 16, 15, and 31 are adjectives modifying the same noun. You see, in other words, combined, the 16/40 that the first fellow gives me and the 15/40 that the second fellow gives me is 31/40 of the total amount. In other words, what that says is that for every $40 I spend, they're going to give me $31. So if I spend $80, they're going to give me $31 twice. Do you see how I'm thinking whole numbers, even though I'm writing fractions? That's how this goes on. Let's try a few more problems, or let's even look to see how this looks, first of all, in the formal way of doing this. You see, this problem that I just did. I'm a math specialist, okay? The problem I just did used the horizontal form. In any arithmetic problem, unless you're using a calculator, people like to use the vertical form. So the way this problem would appear in a typical textbook is it would say 2/5 plus 3/8, and the problem would be written this way. Now you see, what you're going to do here is on the top one, you're going to multiply numerator and denominator by 8. See, 5 goes into 48 times. 8 times 2 is 16. You're going to multiply the second one, numerator and denominator, by 5. See, 8 goes into 45 times. 5 times 3 is 15. So you convert both fractions to a common denomination. Now you see, you can add the numerators, which gives me what? 31. And what's the denomination? 40. But that becomes, see, 40th becomes a 40 in the denominator. See, this is read as what? 31/40. You start to get the idea this way? Let's do another one just to make sure you get the idea. How much is 1/2 plus 1/3? Again, you see, the 1 here is an adjective modifying halves. The 1 here is an adjective modifying thirds. Since the ones are modifying different adjectives, different nouns, we can't add them. We have to find a common denomination. What number is divisible by both 2 and 3? 6. So at a rate of 1 out of 2, you'd be taking 3 out of every 6. At the rate of 1 out of 3, you'd be taking 2 out of every 6. How do you know that? Because 2 goes into 6 3 times. 3 times 1 gives me 3. 3 goes into 6 twice, you see. If I multiply downstairs by 2, I multiply upstairs by 2. That gives me 2/6. And how much is 3/6 plus 2/6? See, 6th is the noun here. 3 plus 2 is 5, so 3/6 plus 2/6 is 5/6. Again, if this bothers you, take a few seconds and write 3/6 this way. Write 2/6 this way. Now you see what? The 3 and 2 are whole numbers here. These aren't fractions. These are whole numbers. It adds up to 5. 5 of what? The common denomination. And you see, the proof of the pudding is going to be how this works in the real world. Let's pick a noun for 1/2, 1/3, and 5/6 to modify that we're comfortable with. How about 1/2 hour plus 1/3 of an hour? See, according to what we just did here, a half of an hour plus a third of an hour should be 5/6 of an hour. Let's translate that into the language of minutes and see what happens. How many minutes is a half hour? 60 minutes divided by 2 is 30 minutes. What's a third of an hour? 60 minutes divided by 3 is 20. What's 5/6 of an hour? 60 divided by 6 is 10. 10 times 5 is 50. Is this now a true statement in minutes? Sure, 30 minutes plus 20 minutes is 50 minutes. Isn't that exciting? This looks like a fraction problem, but it's really what? A whole number problem if I convert my noun from hours to minutes. And by the way, let me give you a warning here. You see, people look at this problem and they say to me, hey, Herb, there's an easier way to do this problem. I say, what's that? He says, well, you just add the 2 numerators and you just add the 2 denominators. The guy says, and that's the right answer. First of all, is 1 plus 1 2? Sure. Is 2 plus 3 5? Yes. But is this the right way to do the problem? No. Why is it the wrong way? Not because I say so, but because it doesn't work in the real world. You see, if this were a correct statement, oh, by the way, let me just teach you some new notation here. If I take an equal sign and put a slash through it, it means not equal. See, 1/2 plus 1/3 is not equal to 2/5, even though 1 plus 1 is 2 and 2 plus 3 is 5. And what I'm saying is, suppose this were true, wouldn't that say that 1/2 of an hour plus 1/3 of an hour has to be 2/5 of an hour? Translate that into minutes, and you'll see that you get a ridiculous statement. See, a half hour is still 30 minutes. A third of an hour is still 20 minutes. What's 2/5 of an hour? See, 60 divided by 5 is 12. 12 times 2 is 24. Look what this statement says. It says 30 minutes plus 20 minutes is 24 minutes. That's ridiculous. In other words, this formula would have been nice, but it's necessary that we don't use it. I would like to just emphasize this for you. I call it the 2 N's, nice versus necessary. When there's a conflict between the nice and the necessary, morality and the work ethic and our social nature requires that we do the necessary at the expense of the nice. You see, if we want our answer to 1/2 plus 1/3 to agree with the physical world, the answer has to be 5/6, even though it would have been nicer to have just added the numerators and added the denominators. And again, in the vein of nice versus necessary, let me show you another example. Suppose I said, how much is 5/18 plus 2/27? Again, what do I need here? The 5 is modifying 18ths, the 2 is modifying 27ths, so I need a common denomination. Well, notice that 18 times 27 would be the 27th multiple of 18 and also the 18th multiple of 27. If I multiply this out, 27 times 18 happens to be 486. Now what do? I convert to the common denominator. 18 goes into 486 27 times. By the way, you wonder how did I get that fast? The answer is, how did I get to 486? I multiplied the 18 by the 27. See, this denominator got multiplied by this denominator. But if I multiply downstairs by 27, I have to multiply upstairs by 27. 5 times 27 is 135. In other words, at a rate of 5 out of every 18, I'm taking 135 out of every 486. And doesn't that get psychologically more complicated to keep track of? Doesn't it seem easier to say I took 5 out of 18 rather than 135 out of every 486? But the reason I'm doing that is I need a common denomination. See, what do I have to multiply 27 by to get 486? I could take 486 and long division-wise divide that by 27, but the easier way is to remember what? I got this by multiplying 27 by 18. If I multiply downstairs by 18, I have to multiply upstairs by 18. So at a rate of 2 out of 27, I'm taking 36 out of every 486. So how do I add now? Since I have a common denomination, I add the adjectives, the numerators. See, 135 plus 36. That's a whole number problem. That's 171. 171 what? See, there's my denomination. 171, 486. By the way, I'm going to show you how to get this later. But it's interesting that 171 is the same as 19 times 9, whereas 486 is the same as 54 times 9. And what that means is, since I've multiplied numerator and denominator by the same amount, I can divide numerator and denominator by the same amount, namely 9, and what I'm left with is what? 19/54. In other words, if one person gave me 5/18 of my expenses, another person gave me 2/27 of my expenses, between the both of them, they would be giving me 19 out of every $54 that I spent. But the interesting point is, how did I wind up with 54 over here when it seemed to me I needed 486? See, when I multiplied the 18 by the 27, the point is I was finding a common multiple of 18 and 27. That's very important. Whereas it's necessary to have a common denomination, it's sometimes nice to have the smallest common denomination. Because the smaller the number, the less chance there is you're going to make an arithmetical error. Of course, with the advent of calculators, that doesn't make as much difference as it used to make. But let me show you something kind of interesting. If I were to count by 18s, you notice what happens over here? 18, 36, 54, 72. And if I were to count by 27s, I get 27, 54, 81, 108. Do you notice a common multiple of 18 and 27 already? Look what I'm saying here. 54 is the second multiple of 18. I'm sorry, the third multiple of 18 and the second multiple of 27. In fact, notice that every multiple of 54 will also be a common multiple of 18 and 27. See, what's twice 54? Twice 54 is 108. You see, what's going to happen over here is when I count by 18s, 486 will come up on my list. And when I count by 27s, 486 will come up on my list. But 486 won't come up until the 18th number over here and the 27th number over here. But you see, 486 is the 27th multiple of 18, or the 18th multiple of 27. You see, but 486 was also what? The 9th multiple of 54. See, when I took the 9th multiple of 54, I went much further than I had to. See, I could have used 54, and watch how much easier this problem would have been. See, does 18 go into 54? Sure, 3 times. Multiply downstairs by 3, multiply upstairs by 3. 5 times 3 is 15. So at a rate of 5 out of 18, I'm taking 15 out of every 54. Does 27 go into 54? Sure, 2 times. Multiply downstairs by 2, have to multiply upstairs by 2. 2 times 2 is 4. So at a rate of 2 out of 27, I'm taking 4 out of every 54. And do you hear how this sounds like whole numbers? 4 out of 54. 4 is a whole number, 54 is a whole number. How many have I taken all together? 15 out of 54 plus 4 more out of 54 gives me what? 19 out of 54. And if you notice, isn't that exactly the same answer I got over here? But look how much easier the work was this way. But now you see the question is, how can you be smart enough to find the 54 without going through listing these things? And that's what I'm going to show you next. It's something called prime numbers, and I want to lead into it in the following way. Suppose I told you that the blank stood for whole numbers, and I say I multiplied 2 whole numbers and the answer is 2. What 2 whole numbers multiplied together give me 2? Well, I think you can see that the only answer is 2 and 1. By the way, order isn't important. I can either write it as 2 times 1 or 1 times 2. In other words, 2 doesn't appear as an answer to a multiplication problem except on the 1 table or the 2 table. What if I told you that the product of 2 whole numbers was 3? Could you tell me then what the 2 whole numbers had to be? Well, the only 2 numbers that multiply out to 3 are 3 and 1. In other words, 3 appears in the 3 table and in the 1 table. But now suppose I told you that I multiplied 2 whole numbers by the 2 whole numbers and got 12 as the answer. Well, certainly 12 times 1 would be one possibility. But wouldn't 6 times 2 also be a possibility? See, doesn't 12 appear as an answer in the 6 table and in the 2 table? Doesn't it also appear as an answer in the 4 table and the 3 table? You see, the problem is numbers like 2 and 3 can only be written as multiples of themselves and 1. On the other hand, 12 can be written as a multiple of itself and 1, but also as a multiple of what? 2, 3, 4, or 6. See, any whole number is a multiple of 1 in itself. But some whole numbers are only multiples of 1 in themselves. And those type of whole numbers are given special names. They are called prime numbers. See, 2 and 3 would be called prime numbers. 12 is not a prime number. It's called a composite number. Let me show you, by the way, how you can find prime numbers. Suppose I wanted to find all the prime numbers that were less than 20. We throw away 1 because every number is a multiple of 1. That would be boring. The next number I come to is 2. 2 must be a prime number because there are no other numbers except 1 that can divide into it. But now every multiple of 2 can't be a prime number because it's divisible by 2. See, for example, 4 is 2 times 2, 6 is 2 times 3. They're not prime numbers, so what I can now do is cross out every multiple of 2. See, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now I come back to this list and circle the first number that still hasn't been crossed out or circled. That's a 3. 3 must be prime because if it weren't, it would have been a multiple of a previous number and would already have been crossed out. So now we cross out what? The multiples of 3. 6 is already gone, 9 goes, 12 is gone, 15 goes, 18 is already gone. Now we circle the next number, which is 5. We cross out 10, 15, 20, they're already gone. 7 is the next number, 7, 14, 21, that's not even on this list. In fact, you see, from here on in, all the numbers that are left must be primes because they haven't been crossed out yet. In other words, the first few prime numbers are 2, 3, 5, 7, 11, 13, 17, and 19. That means these numbers cannot come up in a multiplication table other than where? In the ones table and their own table. Now, I'll tell you why prime numbers are important. 4 is not a multiple of 6. 9 is not a multiple of 6. But 4 times 9, which is 36, is a multiple of 6. Where did this come from? Well, you see, 4 breaks down into 2 times 2. 9 breaks down into 3 times 3. You see the 2 from the 4 and the 3 from the 9 merge to give you a 6. You see, 12 was 2 times 6. It was also 4 times 3. But if I break 12 down into prime numbers as factors, you see the 6 can be broken down further into 2 times 3. The 4 here can be broken down further into 2 times 2. And you see, when I do this, the 12 turns out in both cases to be what? 2 times 2 times 3. See, in fact, what you can do here is, starting with 12, divide by 2, you get 6. Divide by 2 again, you get 3. If you multiply these prime numbers together, 3 times 2 is 6, times 2 is 12. That gives you 12 as a product of prime numbers. You see, the trick here, and I leave the details to you, is if we break 18 down into a product of prime numbers, it's 2 times 9. 9 is 3 times 3. So 18 is 2 times 3 times 3. See, 2 times 3 is 6, times 3 is 18. 27 is 3 times 9. 9 is 3 times 3. So 27 breaks down into 3 times 3 times 3. Now, suppose I want to find the smallest multiple of 18 and 27. What I say is, look, for 18 to go into the number has to at least have what? 2 times 3 times 3. What do I need for 27 to go into a number? 3 times 3 times 3. I need 3 factors of 3. Well, I already have 2 factors of 3 here. How many more do I need? Just 1 more. You see, this part gives me the 18. This part gives me the 27. What do I have altogether? 2 times 3 is 6. 6 times 3 is 18. 8 times 3 is 54. That's the number I was looking for before. Suppose somebody said to me, hey, what's the least common multiple of 18, 27, and 45? See, I break 45 down into prime factors. See, if a number ends in a 5, it's divisible by 5. 5 goes into 45 9 times. 3 goes into 9 3 times. So 45 is 3 times 3 times 5. Now look at, up here I already had what? 2 times 3 times 3 times 3. What do I need for 45 to go into a number? I need 2 3s and a 5. Well, I already have the 2 3s. All I need is the 5. So if I multiply 2 times 3, which is 6, times 3 is 18, times 3 is 54, times 5 would be 270. 270 is the least common multiple of 18, 27, and 45. In fact, just to see how this thing works, see, 270 can be written this way. See, 18 is this much. What's left when you take the 18 out? 3 times 5 is 15, so 270 is 18 times 15. In a similar way, 270 is also what? Cross out the 27, 3 times 3 times 3. What's left is 2 times 5, which is 10, so 270 is 27 times 10. On the other hand, 45 goes into 270 6 times, because if you cross out the 2 3s and the 5, you're left with 2 times 3, you see, which is 6. In other words, 270 is what? If you were counting by 18ths, it would be the 15th number you came to. If you were counting by 27s, it would be the 10th number you came to. If you were counting by 45s, it would be the 6th number you came to. But look how much easier it is to do the problem this way. So now if somebody were to say to you, how much is 5 18ths plus 2 27ths plus 4 45ths? You do the same thing as before. We always work by addition by knowing how to add 2 numbers at a time. What we do is we've just found that 270 is a common denominator. See, we see how many 18ths there are in 270. See, it goes 15 times. See, 5 out of 18 is the same as 75 out of every 270, you see. 2 out of every 27 would be the same as 20 out of every 270, and 4 out of every 45 would be the same as 24 out of every 270. Now you add the numerators, 75, 20, and 24 is 104. The common denominator is 270. So in other words, if somebody was paying 5 18ths of your expenses, and somebody else was paying 2 27ths of your expenses, and somebody else was paying 4 45ths of your expenses, altogether they would be paying what? $104, which is a whole number, out of every $270 that you spent. Do you start to see the idea? And once you see this idea, everything else works the same way as with whole numbers. You still have to have reading comprehension. Look at this problem. It says, what must we add to 3/4 to get 11/13 as a sum? Don't add 3/4 and 11/13 here. Read the problem carefully. It says 3/4 plus what is 11/13. This looks like an addition problem, but it's really what? A subtraction problem. We really want what? 11/13 minus 3/4. And we subtract with the same principle that we add. We find a common denomination. 13 times 4 is 52. Leaving the details to you, 11 out of 13 is the same as 44 out of 52. 3 out of 4 is the same as 39 out of 52. If I take 44 50-seconds and subtract 39 50-seconds, the answer is 5 50-seconds. You see, we still subtract the whole numbers as long as they're what? Adjectives modifying the same noun. In other words, the number that we have to add on to 3/4 to get 11/13 is 5 50-seconds. By the way, there is one little detail I'd like to go through with you right now. When we're looking for prime numbers, it's easy to recognize the multiples of 2. They end in 0, 2, 4, 6, or 8. It's also easy to recognize the multiples of 5. They end in 0 or 5. I thought I would like to show you a nice little mathematical result. It's a cute riddle that also shows you how you can test for multiples of 3. The teacher gave a second grade class a multiplication table to memorize. She asked them to memorize the 9 table. The little boy went home and forgot to do his homework. When he came back to school the next day, the teacher gave them this problem, and the kid decided, gee, I didn't study, but I do know that 9 times 1 is 9. The least I can do, since I was a bad boy, is I'll correct my paper for the teacher. I'll count the number I got wrong. 1, 2, 3, 4, 5, 6, 7, 8. Then the youngster said, but the way my luck is going today, I probably even counted wrong, so I had better double check. 1, 2, 3, 4, 5, 6, 7, 8. And he passed in the paper and got 100. Now what happened over here? Let me put a 0 over here for effect. Do you see that the sum of the digits here is 9? Look what happens over here. The tens digit is going up by 1. The ones digit is coming down by 1. If I add 10 and subtract 1, isn't that the same as adding 9 onto the number each time? See, notice that the sum of the digits is staying the same because the tens digit is going up by 1, the ones digit is going down by 1, but the sum of the digits is always remaining at 9. In other words, the test to see if a number is divisible by 9 is to see whether the sum of the digits is divisible by 9. And that's exactly what I did over here when I had 171 over 486. See, 1 plus 7 plus 1 adds up to 9, which is a multiple of 9. 4 plus 8 plus 6. That's 12 plus 6 is 18. That's also a multiple of 9. And see, in other words, a number is divisible by 9 if and only if the sum of its digits is divisible by 9. And the same thing happens for 3. To test to see whether a number is divisible by 3, just add its digits. And if the sum of the digits is divisible by 3, the number will be divisible by 3. And we're coming just about to the end of our lesson and our discussion for today, so let me wrap it up. And the moral of today's lesson is, again, the more things change, the more they stay the same. If we take this whole lecture, which ran kind of long, and summarize it, all we really said was to add 2 or more common fractions. First of all, rewrite them with common denominators, and after you've done that, add the numerators and keep the common denominator. And do you remember, in our very first introductory lecture, we asked the question, how much was a dime, a quarter, and a nickel? And what did we say in that case? Switch everything to a common denomination. See, 25 cents, 10 cents, and 5 cents. Add the adjectives, add the numerators, 25 plus 10 plus 5 is 40, and keep the common denomination, which is cents. In other words, to wrap this whole thing up, notice that in the quarter, dime, and nickel problem, we see a graphic illustration where by choosing cents as the noun rather than dollars, we deal with whole number adjectives rather than with fractional adjectives. That's a wrap for today. Read the material carefully, do the exercise sets, study hard. As I said before, stay young, have fun. Come back if you have any trouble with this, when in our next lecture we will go through exercise set 4, Form B.